Okay, Cappuccino, for those of you who didn't get to take the notes in class today, let me just briefly show them to you so you can copy them down. We started talking about what is a position vector. A position vector is a vector that starts at the origin. So if you haven't, the origin, we call it letter O. So if you have a vector starting from letter O, so for example, OA, so I'm going from point O to point A, we call that a position vector. So it has some relationship to the origin. Most of the time, we don't really care where the origin is when we're talking about vectors. We're just talking about a shift. How is this point moving from one location to another? How far is it moving left, right? How far is it moving up, down? But if you do have a position vector, then it is tying it to the origin. Okay, so one way of writing a position vector is writing it as O and the point that it's going to. Another way is just referring to it with a lowercase letter. Any vector can be referred to with a lowercase letter. And then we put the little arrow on top of it to indicate that it's a vector. Okay, so we have two position vectors here. We have position vector A, which is 6, 1 over 6 up 1. And we have position vector B, which is to the left 2 up 5. So OB is negative 2, 5. Okay, and we can make the resultant vector AB. We can do that by taking vector B and subtracting vector A, or doing the opposite of vector A and adding B. So that was what we discovered from the warm-up, that the fast way of making a vector between 2 points is to take the ending point, okay, where the arrowhead is, and subtract from it the starting point. Okay, so these were this was the vector components of the B, and this was the vector components of the A. You just subtract them and you get your resultant vector. All right, we also talked about the triangle law. If you have two vectors, say AB, which is 3, 2, and BC, negative 1, 3, and you add them together, you end up getting the result going from A straight to C. So if you add two vectors together, you get what's called the resultant vector, which takes you directly from the starting point to the ending point. And we can do that by just adding the components. So the component of AB plus the component of BC gives me my resultant vector of 2, 5. So you can see going straight from A to C, I have to go to the right 2 and up 5. There's my resultant vector. All right, now when you're using this triangle law, you have to be careful that the two inner letters here have to match. Okay, the head here has to match the tail over here when you're adding them together. So if I gave you this example, AB and CB, and I want to find AC, well, I can't just do AB plus CB because the B doesn't match the C. So what we had to do is we had to reverse the order of the letters here. I had to put the B first and the C second. So when I do that, I'm changing the direction of the vector. So I did that over here. Here's BC going from B to C, and here's going from C to B. These are opposite vectors because they have the same magnitude, but they're going in opposite directions. So BC is negative 3, positive 2, and CB is positive 3, negative 2. So you can see the difference between these is that you just change the signs on the components. So if you change the order of the letters in the vector, the starting point and the ending point, then you just change the sign. So 3 became negative 3, negative 2 became 2. Now I can add AB plus BC because the end of this one is the same as the beginning of this vector. So now I can add those together, see how those match, and that will lead me to the resultant vector AC, the starting point here and the ending point here. And then I can add those together. AB is 2, 1, BC is negative 3, 2, and I get my resultant vector of negative 1, 3. Okay, so here's just a little vocabulary. CB and BC are opposite vectors. Okay, they have the same magnitude, they're the same length, but they're just going in different directions. So if you have the components of BC, you can just multiply them by negative 1 to get CB, and vice versa. If you had CB, you can multiply it by negative 1 to get the opposite vector, BC. These are opposite vectors. All right, so here is what we need also for tonight's homework. Magnitude is the length of a vector. So we can do this two ways. We can use the Pythagorean theorem to find the length of this vector. So I just graphed this vector AB. I want to find its magnitude. So magnitude is just how long is it? How long is this vector? Because a vector represents a direction, but it also represents a magnitude. It has a magnitude, which is represented by its length. So magnitude equals length. How long is this? So if I went 3 units this way, and I went 4 units up, and notice I have my beautiful right triangle. So I could use the Pythagorean theorem and say 3 squared plus 4 squared is equal to c squared. And you should recognize this as the Pythagorean triple, 3, 4, 5. If you don't believe me, go ahead and do the math. But you'll get that c is equal to 5. Okay, so that means the magnitude of AB is equal to 5. So how do we write magnitude? We write it like this. If I want to know the magnitude, we say absolute value of AB. That means magnitude. Okay, so the absolute value bars on a vector means magnitude. Okay, so absolute value bars means magnitude. That is the notation. Again, if you were to go back and look at the video, the first video I showed you with the British professor, he had double bars, but this is what we use in our textbook, okay? But you should be aware that different countries, different textbook publishers might use different notation. But this is how we will be referring to magnitude, is by showing it like this, okay? Another way you might see this is instead of writing AB, you could write the component. So if you wrote absolute value 3, 4, that would mean what's the absolute value of the vector that has components 3, 4, and that would also equal 5. Okay, so that's another way of saying that. Okay, so again, back to our formula packet. You will see this in the formula packet. In another, oh, sorry, I'm jumping ahead of myself. Before we get to the formula packet, I just want to point out, look what happened here. We had 3 squared plus 4 squared. Notice that's my 3, that's my 4. So there's a fast way of doing this. If I want to find the magnitude and I have the component form, all I got to do is I can just use the distance formula. Okay, so I can just simplify this. So AB, the magnitude, is also, we can just say it's going to be 3 squared plus 4 squared, and then take the square root of it. Okay, so that's another way of writing it. In general, what you'll see in the formula packet is they use the letter V for vector. So the formula that you'll see in the packet is the absolute value of vector V is equal to, now this is the first component and this is the second component. So the way they refer to these is they write it like this. They'd say V1, the first component squared, plus V2 sub 2 is the second component squared. Okay, and that would be for 2-dimensional space. As I mentioned, though, we can also do this for 3-dimensional space, like we did in our warm-up with the pencil inside the box. That pencil was a vector. It had a length and it had a direction. And the shift from one end of the pencil to the other end of the pencil could be written as a vector. So if you have 3-dimensional space, you can also do the same thing. It's the square root of the first component squared plus the second component squared plus the third component squared. And that'll give you the magnitude. So this just comes from the Pythagorean theorem, okay, as I demonstrated here. And these are the formulas that we have in our formula packet. Although I just noticed they only put it with 3 dimensions, but if it's 2 dimensions, that just means there's no third dimension. So it would just be the first 2. Okay, so this is the X shift, the Y shift, and the Z shift. So if we look back at our warm-up with the pencil, just to digress a little bit, if I can find my pencil, here it is. So I was saying that you could write this as a vector in three-dimensional space. Okay, it's a shift of 9 in the x direction, 6 in the y direction, and 5 in the z direction. Okay, so here it is. And so then we can just do 9 squared plus 6 squared plus 5 squared, add them together, and take the square root. So really simple finding the magnitude of a vector. If you have the components of a vector, super easy to find its magnitude. Okay, we're just using the distance formula, which comes from the Pythagorean theorem. Okay, and then I was asked, well, can't we just do the Pythagorean theorem? Sure, you can, but sometimes it's simpler just to use one of these distance formulas. Okay, they come from the exact same place. They mean the same thing. All right. Okay, the next thing that we need to be able to do besides take magnitude is there is another way of writing the directions of a vector. So besides using the shift x and the shift y, you can be given the information as the magnitude and then a compass direction. So in other words, a number of degrees. So we need to be able to convert that to component form. Component form, when vectors are written in component form like this, it's really easy to do a lot of math with them. But if you're given a vector in another form, which is magnitude and direction, then it can be a little bit difficult. So we're going to look at changing magnitude and direction to component form. Okay, so let me give you an example. So let's write this down. Change magnitude. So if we know the magnitude, how do we write the vector? So change magnitude and direction, which is going to be given to you in degrees. So like compass direction into component form. Because when it's in component form, we can do some mathematics on it much easier. You know, like adding vectors. Okay, so why is that on my screen? All right, so we are, you could be given a vector. So say I'm given a vector, and by the way, this is not going to be drawn to scale. I'm just going to sketch a vector on here. Let's make it like not do anything pretty so you can't try and count spaces. Here's a vector, and if I tell you that this vector, let's call this vector v. Vector v has a magnitude of 8, and it is an angle of 35 degrees. Okay, so whenever we're talking about the angle, it's just like when we're on the unit circle, that's to the x-axis. Okay, so right here, it's going to have an angle of 35 degrees with the x-axis. So here's my vector. It's got a magnitude of 8, and this angle right here is 35 degrees. So you could be given this information. It's more often that you're going to be given information to the north, and they call that a bearing, but we'll do another example of that a little bit later. Okay, so if I have the magnitude is 8, that means that this length is 8. So I can go ahead and label this as 8. And I know that this angle with the x-axis is 35 degrees. So what I want to do is I want to figure out, well, what would be the x and what would be the y value? And we can do that quite simply using SOHCAHTOA. Okay, so I am going to change this just into a nice little right triangle. So I'm going to, here's my 8. And I'm going to just drop straight down a vertical and drop straight over a horizontal. So I have a right triangle. And I know this is 35 degrees, and I need to find my x value, my x coordinate, and I need to find my y coordinate. And this is super simple, okay? We can use our SOHCAHTOA. So this is going to be, if I want to solve for x, okay, so let's find x first. I'm going to use cosine. So I know cosine of 35 is equal to x over 8, adjacent over hypotenuse. Okay, so we're going to use trig. Okay, SOHCAHTOA. We can just use SOHCAHTOA to help us solve these. So to get x by itself, I just need to multiply both sides by 8. So I'm going to get x is equal to 8 times cosine of 35. And then I'm also going to find y. So y is over here. That's opposite the 35. So I'm going to have cosine, oops, sorry. So that's going to be sine. Sine of 35 is going to be equal to y over 8, opposite over hypotenuse. Solve for y, multiply both sides by 8. So I'm going to get 8 times sine of 35 is equal to y. So now here is my x component and here is my y component. So in component form, I can now write vector v. Okay, notice it's a lowercase v. We can refer to vectors with a single letter. We just use lowercase. Is equal to, and its component form is going to be the x is going to be 8 times the cosine of 35, and the y is 8 times the sine of 35. Bam! And there you have it. And if I simplify that on my calculator, I'm going to get some lovely decimals. So where is my calculator? There it is. So if I put this into my calculator, I'm going to have 8 times cosine of 35. Now, be careful. Make sure that you're in degrees. We're not going to do radians again until later on in the textbook. We're sticking with degrees right now. So my component form would be 6.55. Notice I have to round it off to 3 significant figures. So if I want an exact answer, I would just leave it like this. Leave it with the cosine and sine intact. Okay, and then the other one is 8 times sine of 35. And we get 4.59. Okay, and there it is. So if I'm given a vector and I know its magnitude and I know the angle or any angle, like it might say the angle to the north, if they give you a bearing, so if something has a magnitude of 8 and a bearing of 35, that would mean from the north. So you would have to figure out, it means clockwise, from the north when they use bearing. Okay, so let me give an example of that. If they use bearing, okay, so for example, I'm just going to set it up. Magnitude of, let's say, 15 with a bearing of 120 degrees. Okay, what does that mean? I'm just going to do the setup on this one. We're not going to solve it all the way out because it's just using trigonometry. So that would mean I'm going to figure out my bearing. Bearing means from the north. So if you have a bearing, you have to find north. North we always point as vertical here. And then you want 120 degrees from this. So if I go east, that's 90 degrees. Okay, so here's 90 degrees. And then I'm going to need another 30 degrees. So that would be right here. Okay, so from here to here would be my 120 degrees. So this is going to end up being my vector right here after I've moved the 120 degrees. So I've moved 120 degrees, and now this is going to have a magnitude of 15. So if I was to solve this now, I could do my x and y right here. Here's my little triangle. So here's my x, and here's my y. Oh, what the heck? Let's go ahead and do this. So my vector, the component, is going to be, so for my x, it's going to be, this is going to be 30 degrees in here, right? Because this is 90, and this is another 30 degrees. So right here, I figured out that's going to be 30 degrees because this is 90. 90 plus 30 is 120. So I could say that x is going to be 15 times cosine of 30. So just like up here, so I'm going to have 15 times cosine of 30. And then the other one is going to be 15 times the sine of 30. And that would be if I put those into my calculator. That would get me my vector components. Okay, so that's just switching from magnitude and direction into component form. And then we can do more math. It's easier to do the math when it's in component form. Because if I wanted to add this vector, say to this vector up here, holy cow, if I've got 8 and 35 and I got 15 and 120, what am I going to do with those? Whereas if I have them in component form, oh, super easy. Just add them together. Add your x's, add your y's. Okay, so being able to change from magnitude and direction into component form is very nice for doing calculations. Okay, so you're going to be practicing this in math space today. Okay, but what about going backwards? What if it's in component form and I want it in magnitude and direction? You can certainly do that as well. So we're going to go the other way. Change component form to magnitude and direction. We can do that. And again, it's just using basic trig. So change component form to magnitude and direction. Okay, and direction is we're going to express in degrees. Okay, so let's start out with a vector. Vector v is going to be in component form. We're going to say it's 3 and 2. Okay, so if I go ahead and graph that, so I'm going to have a starting point. I'm going to go 3 to the right and up 2. There's my vector going that way. So here's vector v. Okay, real simple. I can find its magnitude. So the magnitude of vector v, this is going to be, it's 3 and 2, right? So it's going to be the square root of 3 squared plus 2 squared. So you can do it thinking about the Pythagorean theorem or the distance formula, whichever one works for you. That's going to get us our magnitude. So my magnitude of vector v is going to be equal to the square root of 13. I'm just going to leave it like that for right now. Okay, so if I go back to my diagram now, I know now I've got my little right triangle here. This is going to be the square root of 13. So now I need to figure out, okay, I know this is 3, and I know this is 2, and I need to figure out this angle. So all we got to do is do trigonometry backwards, so the inverse function. So which function can I use? I can use any one I want, sine, cosine, or tangent. But notice if I use sine or cosine, then I'm going to have to use the hypotenuse. I'm going to have to use the magnitude, and I could do that. But if I just use tangent is equal to opposite over adjacent, right? So that's just going to be 2 over 3. So I got myself some nice numbers, okay? So from my components, I can just use those component numbers rather than having to mess around with the hypotenuse. All right, so this angle in here, theta, is the tangent of theta is going to be equal to opposite over adjacent, 2 over 3. So I'm going to do inverse of 2 over 3 is going to give me my theta. So I just need to use the inverse function. And if I put that into my calculator, so a little reminder, how do we do that? I do second tan. That's how we get the inverse tan. Second tan, 2 divided by 3. And we get 33.7. So we get the angle is equal to 33.7. Okay, just using, that's degrees. So using our calculator. Okay, so I think that is it that I wanted to cover in our notes for right now. Oh yeah, what about the opposite? What would be the opposite? If I have this as my vector, what if I wanted to know the opposite vector? What if I wanted to know negative, the opposite vector? What is that going to be? Okay, so the opposite would be multiply each of these by -1. So the opposite vector would be -3, -2. Now, what would that be in terms of the angle and the magnitude? Well, the magnitude is going to be the same. It's going to have the same length. So if we think about this, I'm going 3 to the left and then 2 down. So my vector is right here. Okay, and that's still going to be square root of 13. Now remember though, for the angle has to, oops, you can't see that. I am so sorry. Okay, sorry, I'm doing the opposite. What about the opposite of vector v? The opposite is going to be, I just changed the signs on these, -3, -2. So see, it has the same magnitude, but it's going in the different direction. It's going to the left and down rather than to the right and up. So remember though, we need to find the angle in relationship to the x-axis, to right here. So the angle is this. So when we do magnitude and direction, this is going to be my theta. Okay. Now we just figured out, okay, this is 2 and this is 3. So we just figured out that this angle, theta, is going to be 33.7 degrees right there. But I need all this. So notice this is 180 degrees plus that. So you got to be careful when your vector is outside of the first quadrant. You got to be careful about making sure that you're going back to the x-axis and figuring out the full angle. So theta in this case is going to be 180 plus that 33.7. So it's kind of like, when we were using the unit circle and you had to be careful about your signs because as you go around the unit circle, the signs are changing, right? So if we add those together, we get 213.7. So the opposite vector of 3 and 2, the opposite of vector v, the opposite is going to have the same magnitude. So the magnitude is still going to be the square root of 13. That's not going to change. It's still going to have the same magnitude, but the direction is 180 degrees different than this one. Okay, it's 180 degrees the other way. All right, that should be it. Done. Sorry it took so long.